Depending on how your research question is phrased, your study design, or your data collection mechanism, linear regression is not always the right nor the only choice for modeling your data. In this video, I will briefly describe some other common statistical modeling strategies that are used to address research questions of different types, spanning many industries. The models I'll discuss don't even begin to scratch the surface of available modeling strategies. Many of the techniques I will describe overlap with linear regression in terms of the underlying assumptions, how they're implemented, and how the results are interpreted. By the end of the video, you will have a better understanding of when each of these strategies is appropriate to use. As you build your data literacy skills, I hope that you'll further explore some of these strategies and learn how to implement them using R. The first approach that we'll discuss is logistic regression, which is most commonly used when the target variable takes on one of two values. Some examples where logistic regression would be a good modeling approach are using customer data to predict whether someone will default on a loan payment, predicting if a customer will or will not make a purchase, determining the chance of a sports team winning a game or match, or classifying disease tumors as benign or malignant. In each of these examples, we use data from other variables in the dataset to determine which are most important to help explain how you classify data into one outcome category or the other. For example, if our research question for the World Health Organization dataset was phrased as, "What are some defining characteristics of developed countries?" Then the variable status, a character variable that can only take on two values, would be our target variable. Instead of predicting or explaining some continuous numeric value, we would want to make statements regarding the probability of a country being classified as developed or not. The equation we would model looks like this. The right side is very similar to what we observed in linear regression. We have an intercept coefficient given by beta 0, and then each variable, x1 to xn, has its own coefficient. On the left, we are modeling the log odds of the probability of a country being classified as developed. To implement this model in R, instead of using the LM function, we would use GLM, which stands for Generalized Linear Model. We would first need to wrangle our status variable, or create a new variable, such that countries with a developed status have a numeric value of 1, and developing countries have a value of 0. If we call this variable status_01, then we could use the code below to fit a logistic regression model with 6 predictors. The output for logistic regression is also very similar to linear regression, but the interpretation of coefficient estimates is different. Positive estimates increase the log odds of classifying a country as developed, while negative estimates decrease the log odds of classifying a country as developed. There are ways to configure the output so that you can make interpretations using odds ratios. If you would like to learn more beyond this brief overview, on this slide I provided links to some tutorials and articles that offer gentle introductions to the theory and implementation of logistic regression. Earlier this week, we learned how to apply a t-test to compare values of a numeric variable across two categories of a character variable. In cases where the character variable contains more than two groups or categories, then analysis of variance, or ANOVA, is a testing technique that can be used to answer the question, is the mean value of the numeric variable essentially the same across each group? ANOVA also has a lot of overlap with linear regression, as it can also be used to relate a numeric variable to multiple predictor variables. ANOVA is also used as a technique to compare multiple models to each other. Recalling our World Health Organization data, we started with 9 columns of data for 194 countries, all representing information from the year 2015. Suppose we had the same data on the same variables across multiple years. We could then ask more complex questions about trends in life expectancy over time. Whether these trends were linear or not, we could apply sophisticated techniques to model patterns over time for the same country as well as between countries. A similar example arises often in education research. You may be interested in tracking a performance metric across classrooms, within and across grade levels, schools, and school districts. Having this hierarchical structure violates the linear regression assumption that your rows of data are independent. We can use hierarchical modeling to account for the inherent similarities within grade level, schools, and school districts. In medical research, we're often interested in modeling the time until some event happens, such as incidence of disease, death, or recovery from a disease. There are similar examples in areas like engineering when interested in modeling the time until the failure of a device. We can apply time to event or survival analysis techniques to make comparisons between groups and to understand what factors contribute to differences in these event times. All of the previous models we've discussed can be applied within a framework of machine learning. Many organizations that collect and manage large amounts of data use machine learning to quickly find patterns among data. The name describes that the goal is for the computer or machine to learn from the data and improve its algorithms without being explicitly programmed. Imagine a case where you want to be able to detect in real time when someone is committing fraudulent activity with a credit card account. There's an incentive to get your prediction right so that you can mitigate the situation as soon as possible. Additionally, there are consequences for not catching fraud as it happens, as well as for falsely flagging activity on one's account as fraudulent. Modern applications of machine learning include deep learning, where large data sets are modeled through several hidden layers or networks simulating the way information is processed in our brains. These methods require both a lot of data and a lot of computational power. To summarize, we recognize that linear regression does not fit every situation. In this video, we briefly covered some other modeling strategies that help to answer different types of research questions. Each of these techniques can be applied using packages and functions available in R and using other data analysis software programs. My goal here is to expose you to these techniques, knowing that there's so much more involved with each that we simply can't cover them within this short time frame. As you continue mastering the language of data, you will learn the skill of translating a research question in study design into the appropriate modeling strategies.